All right. Hello, everyone. Thanks for making it to the Psyche office hours. Woo woo. I like the cat. Okay. Hi, everyone. My name is Jeffrey Cannell. I also go by Emozilla. I'm one of the co-founders here at News Research and working a lot on the Psyche project. Excited today to just kind of show you everything we've been working on, talk about what we've learned in DevNet so far, what our plans are for mainnet. Some of the areas we're actively working on, and just answering some questions and let everyone know how things are going. So I think we have, looks like everyone's filtering in here. I'm gonna share my screens here. I will make this a little bit bigger for everyone. Okay. So yeah, before we get started, I think, or I get to start out, I kind of wanted to do just a quick review for everyone about exactly like what Psyche is and kind of like what we're trying to do with it and why we even thought it was something that needed to be done. So you may or may not have heard about this. Let me go here. Uh, Llama 4. Okay, what's happening with Llama 4? Um, so, a lot of the open source, a lot of the uh, results that we've seen over the last several years in the open source AI space really are thanks to Llama. I mean, that was really the kick in the rear that got like this open science thing going. And Meta did an incredible service to the world and to the industry when they started releasing the Llama models. And this was kind of great up until about a year ago. We started to ask ourselves the question, like, what happens if we don't get Llama 3 at the time, even? And we're like, oh, okay. And then Llama 3 came out and everything was great. And it looked like for a while that this might keep going on. But what we're starting to see now is that we can't rely on closed labs to just keep feeding us open source models. And because of this, we asked ourselves, is there a credible way that the open source ecosystem, and I mean open source both from a data, from a compute perspective, is there a way we'll ever be able to stay at the frontier, right? To do that, we need models that we make ourselves. And like, how can we get about doing that? So one of the things we identified was that to do this, training a large foundation model, and I'll let everyone remind everyone when AI models are made, basically they kind of come in two stages. The first stage is this thing called a base model, which is where you're basically just training on everything on the internet, books, just the entire corpus of every written word. And this is very kind of like dumb, right? You just go download all the data off the internet and you just shove it into the transformer magic and out comes AI. And the fact that this works kind of is like the crazy thing, right? That you can just have piles of unsupervised data and the transformer architecture can make sense of it, identify patterns, and figure out how to produce the next token. Basically totally magic, right? um, but this is a huge amount of training cost to do. And in particular, this huge amount of training cost is very communication dependent. When you're training these models, you have to basically have all the GPUs send data back and forth to each other over these very expensive like interconnect called InfiniBand or Rocky or these other things, which are at like terabits of gigabits, at least hundreds of gigabits per GPU, in sending to every other GPU. And so because of this, to do the training, you have to basically have all these GPUs sitting in like a giant warehouse, giant data center, right? And this giant data center basically is owned by like one organization, and that's sort of how things are done now. We spent a while trying to figure out, what were the blockers to being able to take the GPUs that everyone has all over the world and use them and have them cooperate together to train a single model. And this communication bottleneck was sort of like the first step. It's not the only step, but it's the first step. So we spent a while working on that, and we were able to develop a couple of algorithms, originally distro and one called later on called demo, that basically figured out a way to reduce this communication overhead by like several orders of magnitude. And the way we did this was taking cues actually largely from some 90s era signals processing stuff, which basically is taking the actual training results and then converting them to something like the JPEG version of them, and then communicating the JPEG version of them. And this seems like kind of like, wow, that seems super simple. Well, like all great ideas, the idea is simple, but the execution isn't where the genius lies, right? But this, too much to our surprise, actually worked. And then we said, okay, so now we actually have a way to cooperate, over the internet and train a true foundation model. And that's when we started the Psyche project in earnest. And what the Psyche project basically is here's a thing that basically shows the outline. Basically what it is all of the code to facilitate this cooperation. So there's the distro algorithm, which is like the base level mathematical technique. And then the Psyche code base is a realization of that and actually does all the training over the internet. And we've been working on that for about a year now, and 2 or 3 months ago we went into DevNet, where we actually started trying to train a real live model. So over here, I'm going to pop us over to the model training that we've been doing. And we chose to train a 40 billion parameter DeepSeek style LLM that's a dense model. And this is kind of a little bit different than maybe some of the models that are I'd say a fair number of the models come out now are these things called MOs, or mixtures of experts. And the thing that mixtures of experts are great because they sort of train faster, but the problem is they have huge parameter counts. And one thing that's always been important to us at Nous, I mean, it's really what got us started in the first place, is local first AI. And I'm talking like local first in that you can run it on your MacBook, you can run it on your, I have a 5090 now, but I had like a 4090 or something like that. Like truly AI that you control and answers only to you. And so to do that, it's important that the model sizes that we train be both, the models need to be powerful, but they also need to be small enough that everyday users can actually touch and use them. And you don't need to go have a $500,000 BGX from NVIDIA to run your model, even if it is theoretically open source. If you can't run it yourself, like is it really, how open is that really? So what we did is we decided to take the DeepSeek architecture and remove all of the mixture of expert elements and just train what is called the dense version. Now, the dense versions they take longer to train, but they sort of like compress the data down tighter into fewer parameters. And this was interesting because one of the novel pieces of DeepSeek is this thing called multi-latent attention, which is a new attention mechanism that increases the inference speed for long context, as well as just training on longer context. And this technique had not been applied to dense models, so we figured, why don't we try to train a DeepSeek style model, but make it dense using MLA, and actually have it be something that was novel and useful. So we started training this about a month and a half ago. We're currently at about 1 trillion tokens trained, and this dashboard here is like a real live dashboard of the model training. You can see our loss curves, some of the benchmarks that we run, and what's cool is that like each one of these little nodes here, it actually represents like a what's called an HGX, which is 8 H100 GPUs. And each one of these little nodes is like costs like 300 grand basically to buy. And these are running at data centers all over the world. And they're communicating actually over the Solana network. So you can actually come onto any one of these and click it, and you can actually go see this address right here actually is this exact HGX somewhere in the world sending all of its messages. They each send transactions over the Solana network to coordinate the training of this 40 billion parameter model. And you ask, why did we choose to do something like this over Solana? Well, and it really came down to two things. One, we didn't want a single point of failure. If you have this great distributed training network, and then you have like one computer that one person controls that like coordinates them all, well, that one computer becomes like a bottleneck, and that's bad like for two reasons. One, we don't want to make it so that if that one computer goes down, like the whole training run dies. That's just like that's not that's one piece of it. But the second one is that for this truly to be decentralized and for it to be owned by everyone, there should not be any one organization that even has the ability to step in and control it. And this was created, and we made this decision in the backdrop of something about a year ago called Senate Bill 1047, which was a law in California that was actually passed the California legislature that would have essentially put this thing called strict scrutiny or strict, not strict scrutiny, I forget the word, but basically what it means is that like if you make a product and someone uses your product to go do something bad, then like you as the maker of the product are liable for that. And this is something that like they don't even put on gun manufacturers, right? And they were going to do this, and it actually was passed the California legislature and would have basically made what open source AI does, what Nous research does, not only illegal, but like put the people who work at Nous or work on this like in jeopardy of law as well. And so we need to have a way that we would be able to distribute this out and have it run in a way. There was no single person who was in control of it. So we use the Solana network to basically as a way for them to communicate without any any centralized party. So we've been continuing on with this training, like I said, for about a month and a half now. And one interesting piece of this model that we're training, you can actually click here and you can actually get like thankfully, Hugging Face has been very kind to us and let us commit all of the checkpoints all the time. But you can go download like at any step, all the way the model, and it'll just run right away. So it's sort of updating live. We up about once a day. It pushes a new checkpoint. And so one of the things that we've been working on is this model is what we'd call like a true base model. And a base model is that thing I talked about at the beginning, which is not the final product that you see. The final product you see is usually what's called InstructTune, where you turn it into the helpful assistant. And on that phase, I'm going to plug right here. Just last week, we released the Hermes 3 dataset. So this is the actual dataset that was used to create Hermes 3. So basically, the way it works is it's something like this. You have base model plus fine tuning plus RL equals final model that you use. So this section right here, this fine tuning here is done by carefully curating data sets. And this was, at the time it was the model was released, this was basically the state of the art training data set for open source. And this base model part right here, though, so like right now it might be Llama 3 plus Hermes 3 plus Atropos equals. But so you'd have a base model here that would be Llama 3, your fine tuning data, which would be the Hermes 3 data set, and then Atropos. We're focusing here on creating this right here, the base model, which is like the true bedrock that everything that comes after. You cannot have anything after it without that. And that's like the most intensive compute part. And so rather than trying to create like a final model that has really good benchmark scores, we're creating like the granite from which we will then apply these instruction tuning methods and RL to like then actually bring out the capabilities that you would finally use. But we got to have this bedrock part. That's like the most important part, is to have the stone out of which we can carve sort of the statue that is the final model. And so one of the things we did was we used some of the open source data sets out there. The three that we are using right now are something called the Stack 2, and also called, or I mean, FineWeb 2 and the Stack. So FineWeb is basically a rip of all of the a filtered version of all of the internet. FineWeb 2 is the same thing, but with hundreds of languages. So what's interesting about the consilience model we're training is a third of the data is multilingual. And so we're making a focus on like creating this foundation-based model that everyone in the world can use. And we've had a lot of fun doing it. We've learned a lot about the actual execution of pulling something like this off, like actually training, a 40 billion parameter model over the internet with hundreds of these different nodes. And to talk a little bit about some of these challenges that we've had, I'm going to bring up our principal engineer on the Psyche network, Ari. Ari?
All right, let's see. Is that working? Hey, folks. I'm Ari. My microphone never works. And I would love to tell you folks about some of the networking and distributed systems issues we encountered and how we got past them when building this stuff. So, Psyche, as like a distributed network, necessarily requires a bunch of peer-to-peer connections between all the nodes in the network. While we can use something like Solana for the actual like high-level coordination, uh, Solana doesn't have the capacity to carry the amount of data we need to actually transmit between participants on the Psyche network. So while we've used our distro demo optimizer to bring the bandwidth down, on the order of 1,000 times smaller, it's still on the order of tens of megabytes per node per step. And if you try and put tens of megabytes per node per step on Solana, you will be paying a lot of money, and you'll probably take the entire network's capacity. So what we've done is build from scratch a peer-to-peer gossip network based on a networking library called IRO. And so I'm going to share my screen real quick, and we can see that we have a lot of pretty graphs. And so what you're all seeing here is like our really low level metrics at what's going on at the network layer for every single one of these Psyche nodes combined. So we've got, on the order of 50 to 100 nodes on Psyche at any given time training. And each of these nodes has to make connections to all the other nodes to talk about communication of like what the training results are, and how to coordinate. Hey, I'm done this. I'm done that. Who am I still waiting for?
Did
So,
Wayland get us?
no, can you see this or no?
No, it just says loading.
All right, let's try again. Any luck?
No bueno.
Okay. Oh, wait, we got a maybe. People say it works. All right. Well, if you can see this, this is a huge series of metrics. Basically everything that's going on at a low level in Psyche. So we've got, all these different nodes doing all this gossip connection stuff back and forth. They're doing like blob downloading. They're doing all sorts of awesome stuff. And so one of the issues we've been running into is that we have been really saturating our bandwidth. So if I pull up, say one of our metrics for every single node, you can see that not every node experiences the same kind of thing across the network, right? We've got, some nodes have different spikes in like the tick rate of the networking stack at different times. Some nodes go on and off. Some nodes will, lose network connections sometimes and actually lose connections to each other. And what this means is like when we're building this stuff, we need this kind of observability on like who's downloading what from who. When things spike, we need to go into our logs and figure out how to debug all of this. So one of the big issues we had, just send a picture of the screen for folks who can't see it. Oh, Tech already got one. Cool. One of the big issues we had is that we find that hole punching a direct connection between two nodes is not an easy thing. Now, thankfully, the IRO team's product has built some awesome stuff that makes this work a lot of the time. But in the early days of the Psyche DevNet run, we had a lot of failures in hole punching. So what we'd end up seeing is nodes sending massive amounts of data over like a relay, which is some server that we have that sits up there and just exists to shuttle data back and forth if two servers couldn't directly connect. Now, because of the amount of data we're shuttling back and forth, even though it's so much smaller than it would be without distro, it's still very, very large. And as a result, getting that hole punching working has been very, very important. So we've done a lot of work with the IRO team to figure out, why are things going wrong in hole punching? When do connections go over the relay? When someone drops off, how do we get them back online? Do we, check for connections? Do we see, hey, what's going on here? When the Hello, Grafana. When the relay starts taking over, how can we get nodes back into direct connections? And my metrics apparently don't work. Here we go. Anymore. So, what we've done through all of this is work with the IRO team, find a bunch of bugs in IRO, find a bunch of bugs in our implementation. All of our code is open source, which I think is, people don't really realize this, but pull up the Psyche GitHub repo. We have every single part of this, like completely open and live right here. You can go look at how the networking stack works. You can go check it out. It's right here. It's all out in the open. All of our pull requests are in the open. All of our issue tracking is in the open. You folks could contribute to Psyche if you so desire. And if you know anything about low-level distributed networking, we would really appreciate if you took a look and told us what we're doing wrong, because as much as we are building this out as an open source lab, we are really supported by the community, right? We couldn't build this without standing on the shoulders of all those who came before us, and we hope to be able to lift up the people who will come after. And we really want Psyche to be the way to be the future-looking pre-training stack, so people can all share in training models together, so we can all get the models we want without having to individually rent, 1,000 H100s. So, built on top of IRO, increased stability in networking every day. We're getting better and better. We've done a lot of work on decreasing bandwidth. Since we started the Psyche project, we've already brought bandwidth down like another significant factor just by doing some compression. Everything is fully reproducible and built with NICs, and we are adding support for building this out in the support in the anticipation that one day this hole punching networking stack will be able to run on any network connection, not just data center links with public IPs, but eventually home computers. And to that end, we're building up support for this hole punching, no port forwarding needed. Psyche is just something you will be able to download and run on any machine that could, in theory, contribute to the network. And so what we're doing right now is just going full on, building this stability out, building this DevNet run out, and figuring out all the kinks. So when it's time to bring this thing, live to a mainnet launch, we want Psyche to be robust and ready to go. Cool. I think that's about it for distributed networking, Jeff.
All right, let me grab the screen back from you. Okay, so now I want to talk a little bit about what we're doing, like right now, the features that we have on our immediate horizon, and the blockers we have towards we're ready to launch this thing sort of on the mainnet for real. We have a couple of items that are top level things. So one of the design choices we made when we wrote this is actually to write the entire code base in Rust. This is maybe a little bit unusual for an AI project, which is usually written in Python. But we chose to write it in Rust because it allowed us to take much better advantage of the multi-threading capabilities. Python is fundamentally like single-threaded up until like the latest 3.12 release, but even then, very difficult to work. We so we decided we wanted like one binary that we would be able to build down to, and it would just be like psyche.exe kind of thing, that you just double click and it just works. So we chose to build in Rust instead of Python because shipping Python is notoriously difficult if you're trying to target sort of end consumer level products, which, like I already said, eventually we want this to be able to be, like folding at home. You run it on your computer at home and you use your GPU to contribute. So we build it in Rust, and all the training code, in fact, is written in Rust. And that code is, if you go like to the, where is it, shared one here, and then to the modeling source, there are models like here's our DeepSeek model that we're training right now, and it's written totally in Rust. But one thing we've discovered over this is that a lot of the ecosystem, the advanced features that are coming out are in PyTorch, or we're using libtorch in this, which is the C++ bindings. The PyTorch version they've been putting more of the features into the Python part, the Py part of PyTorch, rather than the Torch part of Torch, which is written in C++, and we're missing out on that. And so those items are things like FSDP2, fully sharded data parallelism 2, some of the uh, expert parallelism stuff that is happening, that is coming out for upcoming Mo models. Torch.compile, which is like this thing that just makes your model like 20% faster magically. All these things are now like being pushed into the Python side. So what we've actually done, this was a big effort over the last month, was to develop, to basically make the back end of the trainer be fully abstracted out, so we can use different trainers, not just the Python, not just the built-in native Rust trainer that's inside Psyche, but any Python-based trainer. So one of the big PRs we just pulled in is this Pythonification and trainer abstraction one. This was quite involved, but what it'll allow us to do is at Nous, we've actually been commonizing our training stack onto a new, based on a new project called Torch Titan. So Torch Titan is a pre-training framework that is put out by the PyTorch team itself, and sort of has all the latest bells and all the latest bells and whistles, and it has features for all these new things that they put into PyTorch. And so we've actually been commonizing our internal trainer to Torch Titan. And what we're going to do now is take our internal trainer that we use to train both for reinforcement learning, for fine tuning, and for pre-training, which is based on Torch Titan. We're going to take that and we're going to use that as the trainer inside of Psyche. So to do that, we needed this whole Pythonification method that allows the Rust code and the Python code to interact with each other. So now that we've have Python support, Python abstracted Python support within the Rust code base, we are able to use the Torch Titan. We're going to have there's this branch right now called Torch Titan on the Psyche code, which brings in this trainer, which is the Torch Titan based fork, or the fork of Torch Titan that Nous is maintaining. And what's good about that is we're looking like it's basically like a 2x speed up, pretty much, over the current trainer in Rust. So that was basically going to like double our compute throughput just overnight when we merge it. So we're very close on that. So that's one of our blockers for mainnet, is we want to, when we go to mainnet and we're really paying for the compute that we're using, we need to be as efficient and use it to like its fullest capacity. And so getting a state of the art, top of the line pre-training framework in as the backend for that we're coordinating was one of the things that we did. So that's happening right now. Another one that we're going to be putting in, and you will be seeing this very soon in the public dashboard, is we are putting in not only just pre-training, but actual full fine tuning. And this fine tuning code that we have is everything that we've learned about fine tuning at Nous, which includes all the advanced methods like loss masking and signal packing, sequence packing, and all the different things that we do will be all the different things that fine tuning in particular needs will be supported now inside of Psyche as well. And we will be doing a fine tune of a soon to be released Nous model. You might be able to guess what it is. We're going to be running that on the Psyche network. So that will be coming very shortly once we get this fine tuning PR in. And once the fine tuning PR is in, we'll be able to do some cool fine tuning jobs on Psyche as well. I should also note that the Psyche network itself is, while the compute, joining the compute, like if you had the H100s right now, you have to go through us to like get added to that on DevNet. The actual ability to like interact with the contracts is fully permissionless, and anyone's able to interact with the contracts. So we've been working on this Torch Titan piece. We've been working on the Python piece, and then another piece of it is we just got back Well, it was about a couple weeks ago, but we just went through all the items. The second of the two audits of the treasurer. So the treasurer is the piece of code, the Solana code that actually manages making sure that the compute that is brought onto the network gets value distributed back to them proportional to how much they actually put in. So this code we've had written for a while, but this is like, all the load bearing economic code. And if you go into the architectures, decentralized, Solana treasurer, so we had this particular code base here, which this is where people can, like, the people who are running the jobs can claim everything. We've had this now audited by two different teams, both by Zellick and Halburn, and they've given us basically the green light on that. So that was a third of the kind of the last of the pieces that we needed to make sure that the code that autonomously distributes any of the rewards to the compute providers and to the people who are contributing, that all is rock solid, because you can't have any bugs in that. So we paid a lot of money for the audits for that, but it came back good. Vincent, who's like our smart contract dev, has done a great job. Vincent also has put out a bunch of really cool open source packages for the Solana ecosystem that we built up as part of making this. So that's there. So those three things: the treasurer code, getting all the economic code audited and getting the thumb up. Increasing the throughput speed by switching to a state-of-the-art training framework, which again is one that's a fork of Torch Titan that Nous maintains. Those were a few of the last items that we sort of have on our bucket list, and we have PRs for several of them open. You can follow along with what's going. Would also encourage anyone who is interested in helping us out. One way would be to look at some of these PRs that we have and comment on it. And I would love to anyone who wants to contribute to the code base itself. We're definitely looking for contributors on that as well. So that's basically the future roadmap and what we have blocking before we're able to go to mainnet. And the last thing I wanted to do before we sort of open up the floor for questions and discussion is to bring on Bowen, who is our chief scientist. Bowen was the one who originally developed the distro and demo algorithms, and I wanted to give him a couple minutes to talk about some of the futures areas of research that we're looking into to like take Psyche 2.0, kind of to the next level. So what we have here, we also are operationalizing the distro algorithm in Psyche. We're working on some new items that will be able to roll in later. And so without any ado, I'll bring up Bowen.
Yeah, hi, thanks there. So yeah, basically, here Psyche, the goal for Psyche is to become not only like a training or inference platform, it will also be a platform for research and development of future like AI algorithms, especially internally at Nous and possibly also for the open source community. So basically, after that we prove that we can train stably and like very efficiently on this decentralized network, we can now start to change the architecture and try out like new ideas, right? For example, TP over the internet, right? That could be possible. Also, other like pipeline parallelism, PP over the internet, or even MOEs like EP over the internet. Those are like very simple additions to what we currently have, like DP over the internet. And no one has ever like really tried those because no one seems to think that the future of pre-training should be decentralized. Right now, everyone is still training centralized. The newest Kimi 2 model is still like fully centralized. But we do believe that in the future, decentralized training could also be a viable contender to centralized training. And therefore, it is important for us, like basically, try out new, like even more efficient methods of using this kind of architecture of this networking architecture of like the internet, right? Where you have very fast islands and like very slow communication between islands, and you can scale indefinitely, unlike centralized pre-training where all like when you scale up, you get this quadratic problem where all the power and everything needs to go into one place. and that's like more and more expensive. Like it grows by quadratically. Here with the internet, we can take advantage of like distributing everything. So we can take advantage of like power and like cheaper power, cheaper compute across like the world. So yeah, in the future we're probably going to try out new architectures. This pre-training that we currently have is just like a test, just to prove out that we can train an LLM, like a big LLM, to test out scaling laws. In the future. Sorry, I think you mean demo. Yeah, I said like demo. I don't think I said demo. Yeah, I mean yeah. Okay. Yeah. So that's about it.
Yeah, so part of what Nous does is facilitate academic progress in the space as well. That's the team that Bowen leads. If there are any aspiring AI research scientists out there, please reach out to us. We have a researchers in residence program, and we're also hiring full-time academic researchers. So if you're interested in keeping the future of open source AI alive and flourishing, come talk to us because we would love to hire you. Okay, so I think that's everything that we have for the sort of standard piece of it. And what I want to do now is open up the floor to any questions that anyone has. I'm gonna check here. Let's see here. Let me see here. Was the Pythonification done with PyOxide or was it bespoke? Yes, so the Pythonification uses PY03, but we actually had to, it was a little bit involved because the way it works is that there is a main Rust process which internally has an extension that's injected in, and it controls and it has inside of itself a Python interpreter being controlled by the Rust process. So that's like when you embedded the interpreter into the Rust process. So in that case, so there's one master Rust node that is using PyOxide, or it's using PY03 to communicate across the Rust Python boundary. And this is needed so that we can take all the data from the P2P layer and send it out to send it out over all the others, send it out over the network, and then take the data from the network and be able to get it back into the Python side. Then for tensor parallelism and data parallelism, though, if you want to have multiple, the paradigm that Python code's written in is that you actually spawn multiple processes, and then each process gets one GPU. So if you're on like this HGX that has 8 H100s, what you actually end up with is like one Rust process, and then you have 7 Python processes. And those Python processes are actually top-level Python processes, right? And what happens with those ones is we spawn them up. We call them the sidecars. So we'll spawn up like 7 of the Python processes, and then they will load a compiled version of the original Rust code as a Python extension. So it's like a PYD file, or it's a compiled C Python extension that is identical in code to the Rust code that's in the parent, the master process, but it's now been like reversed. And the Python code is the Python process, the top level one. It loads in the library, the Rust library that's compiled, and then they communicate over the internal NVLink within the box, within the actual single node, to share the data that was that the master Rust process got in between there. So it's a little bit of a finagling game, but that's how it works. Okay, let me see what else. Is there a way I can...
We got some interesting questions here. I can pull a couple
go ahead.
out.
I'm just trying to catch up. Yeah.
Yeah. So some people asked, how can this be used for voice AI? That's a good question, actually. In that Psyche is not necessarily stuck on doing just text models. It works with basically anything that's a transformer. So while we're not currently training any voice models on Psyche, there's zero reason why you couldn't put together a voice data set, voice model architecture, and start training a model that does end-to-end voice synthesis or even multimodal voice in and out on Psyche. The point is we're trying to make an infrastructure that is compatible with basically every kind of modern transformer model. And as long as the distro optimizer works with it, which so far it works with basically all the modern large language models out there, that including multimodalities with voice and images and stuff like that. There's no reason we couldn't train a model like that.
And the trainer abstraction that we added in is really going to go a long way here, because rather now than us having to hand code support for all the different types of models and manage it ourselves, as long as it can, you basically have this thin abstraction layer where you just have to write like a simple, there's like an API that the trainer communicates to the master Rust process with. And then as long as that, you can just, write that simple interface, you can use any other trainer basically. And as long as the model itself is like a torch model, and it uses the standard forward backward pass paradigm to calculate the gradients then turn into the distro updates, which are then replicated across all the nodes, and then the updates are applied as if they were the backwards, the application of the backwards pass. As long as it fits into that sort of standard neural network architecture, there's nothing explicitly special about an LLM versus any other modality or even any other architecture, like a non-decoder only transformer, like a classifier or a diffusion model. In fact, we actually don't have it in, but we actually did code up all the code for like a diffusion model and it works with that. And for example, Torch Titan has support for Flux in it natively, which the Flux diffusion model. So like now that we have the train abstraction, we'll be able to do that. There's another one that I see is, has there been any work going into solving the minimum viable contributor issue on distro? I figured out a way to get the minimum viable contributor pretty small. So the minimum viable contributor is basically this idea that every node that joins the network incurs some amount of cost in the network communication. Now we reduce that, but it's like non-zero. And it's a little bit the paradigm's a little bit difficult. It's harder on the internet than it is in a data center, because in a data center, typically, as you increase the number of compute, you're like increasing your bandwidth at a proportional rate by like adding more InfiniBand switches, and the network itself is already like very densely connected. Like within a switch, you'll have like 64 GPUs, and all of them have a link to every other GPU kind of deal. Over the internet, you aren't really fundamentally increasing your bandwidth that's available to you by adding in another node. And so there's a limit between like the amount of when you add a node comes on, it takes a certain amount of network bandwidth that people have to do to send data to it, and then versus how much faster do they make the training run. And so the way you can attack this is in two ways. One is you make your updates smaller, so that ratio between the bandwidth requirements is just the amount that a node adds is smaller. And distro has already done this, and we have ideas for, I guess you could say, like incremental ways of doing this. One thing that we haven't published that much about, but is in the code, is we developed a 1-bit quantization technique for distro that cuts down, that was able to reduce the bandwidth even by like a factor of 4 from the original paper that we had. And a factor of 4 doesn't sound like a lot, but it is when you're dividing. That's the difference between 10 megabytes and 2 megabytes, right? If you go from 10 or 2.5 megabytes, if you go from 10 megabits to 2.5 megabytes, you can now like add 4 times as many nodes, right? So it like even incremental divisors on that number is important. And then the second way you can do that is by somehow altering your networking topology to affect that factor as well. So there's different ways of doing these, like treed all reduces or ring reduces, where like you aren't scaling the network compute usage by a quadratic factor every time you add something, but some sub-quadratic factor that is some n log n or something like that, right? So we're also exploring ways of on the networking side to do both of that by making the updates smaller basically, and then also optimizing the network topology so that you don't have to get as many updates to as many people. So one thing we did in the IRO library, for example, to do this, previously Bowen was talking about these islands, right? Where like you have, if you think about the way the network works, what our networking topology is, inside of a node, like a single node that has 8 H100s on it, those 8 GPUs are like sitting on the same motherboard. They're connected by this thing called NVLink, which is right on the motherboard, and like they basically are like instantly free to talk to each other, right? Like extremely fast, like terabits, so terabits a second between the GPUs. And then that once you get outside of those GPUs, you can talk like maybe 100 megabits a second. So you've got like 3 orders of magnitude like difference between the things there. So you have this island concept where everything's really fast on the island and you're just glacially slow outside of it, right? So we create in the IRO stack, we modified it so that as things come into a data center, if there's any nodes within the data center that are also on the Psyche network, it will try to like quickly distribute all of the distro updates to the nodes that are inside the same data center as another node, right? And this is like in the terminal case, like this may not do anything, but like in the current case now, where there's only like several dozens of data centers, this provided a networking topology speed up because we were able to reduce the networking connection rather than having everyone send to everyone in a data center. You can just like have one person send it to only one person in the data center. In the data center, those people can like replicate it more quickly. So those are the 2 ways we're working on attacking the minimum viable problem.
Jeff, I also want to add that one of the other things we're working on is making Psyche more viable for heterogeneous compute, right? We all have only H100s right now on the network, but ideally we'd like people with different speeds of GPUs to be able to join. And this is kind of like tackling the minimum viable compute problem, because when you think about it, if you've got a GPU that's a smaller, slower GPU and it can't do as much work, we need to figure out a way to both reduce the amount of work that gets assigned to the GPU so it doesn't slow the network down, and figure out how we can reduce the amount of data sent out of that GPU so it doesn't, waste the bandwidth that a faster one would. So we're working on actively scaling that first half. The amount of data passed to each node, making that dynamic. We're using dynamic batch sizes. But the actual, scaling the outputs from a given node is something we're still researching. We haven't done a lot of testing in seeing how much that actually affects the network and how we can take these like different size results. But that is definitely something we're interested in figuring out in the future.
Yeah, I could also add a last thing is that by expanding the training platform of Psyche, we'll eventually be training multiple neural networks at the same time. And some neural networks, like for example, diffusion models, are much more compute heavy than memory heavy, right? So the minimum, basically, the minimum hardware that you need to join will be much lower because that you wouldn't need as much VRAM. There's also other scaling laws of neural networks, like inference training, inference scaling laws, inference time scaling laws, and also like reinforcement learning, where you have a lot of the compute you have to do in a single node and not much like memory. So that could also be a way of reducing because if you have, for example, 3090, you could join a reinforcement learning run of a 14B model, because then you could do inference, but you can't really do training, and you could still contribute to the training, but you wouldn't really be doing training.
Bowen, could you give a quick recap for people who don't know how the 1-bit works, just to explain why we could quantize our distro results down to 1-bit?
Okay, yeah, sure. It's because when you pick basically, so like if I just see it very simply, is that when the distro results are basically picking the top K of the DCT compressed version, right? Like this, not DCT compressed, but DCT transformed. So you basically transform the gradients first with the DCT, and then you do the top K. And when you do the top K, you can think of imagine you had a Gaussian distribution and you pick the top K of 4. All those top Ks would be similar in size, right? Because you would be like in the very tail end of the Gaussian distribution. They'll be very, very big. And those things, they don't really care. We don't really care about their size because they're already like so big. And especially when you only pick like 3 or 4. If you pick like, let's say 1,000, then they wouldn't be the same size. But if you pick like very few of them, they're all like very big. So they're pretty similar. And then if you quantize them to 1 bit, it doesn't really matter because only the direction really matters, right? Because afterwards, when you do the preconditioning, we use the sign SGD to do the preconditioning. But if you used ADAM or whatever, like ADAM, you multiply by the scaling, a running average, right, of the second norm. And if you do that, you basically like normalize back the gradients, right? So if you pick very big gradients, always pick them, and then you normalize them back to 1. Then you can just send the sign. You don't really need to like send the size and then renormalize. So that's basically the overall reasoning behind it.
Makes perfect sense. Thank you. I appreciate that. I wanted to just a question real quick. A lot of people have been asking, how can regular people contribute to training on Psyche? So we really want long term to be able to support all sorts of compute and use it as maximally as possible. We've talked we talked a little bit before about like the idea of folding at home. I don't know if any of you ever tried it, where you could download a program on your computer and leave it running overnight, and it would fold proteins for medical research. There was also SETI at home, which would use your idle time to like analyze radio telescope data and do the search for alien life. And really what we want with Psyche, what we're dreaming about long term, is the ability for anyone to dedicate compute towards a global network of training models. Now, we're starting out with a much more rigorous set of requirements, right? We're doing specifically sized data center computers on like private clouds, and we're connecting those together. But what we're working towards is a fully democratized model where anyone would be able to join on any hardware that past some minimum compute level. And what we're doing, all the work we're doing now, is to bring up, in this testnet, is to increase stability, increase robustness, and get ourselves really confident with the core of what we're building, so future research directions and future development on Psyche can bring us down to a place where anyone could contribute. And while right now the models we're training, right, our 40 billion parameter model, necessarily requires hardware with a bunch of RAM to fit the model in RAM, there is no reason why we can't train smaller models on Psyche, right? The coordination problem with smaller models is like, as we talked about before, like the trade-off between, hey, does adding more compute to this network, if it's slower compute, does it actually make things faster? If we have to do additional uploading and downloading, how do we deal with the slowest bottlenecks if someone has a slow connection? But we are both in a research and an engineering sense working on solutions to all of this, and we are ever moving closer to this end goal of having, AGI at home, where we'll all be able to run Psyche on our home PCs overnight and donate our own compute to help train these models.
Yeah, ultimately, Nous's mission is to create the world's best AI in the open. That's what we're here to do, to create the world's best AI and also to do it in the open. Training and doing the pre-training is one piece of making the world's best AI, but it's actually not all of it. Just as important are things like data synthesis, like what data goes into the model. And this is an area that we're interested in like further expanding within Psyche, and an area in which contributions from other people can be much more realized, whether it's in the data set creation of the actual models that are going in, or as we transition to the reinforcement learning phase. I haven't mentioned this, but I guess once we get to the first sort of milestone after we get to mainnet, we'll be integrating the reinforcement learning mechanism into Psyche. And on that, it's much more amenable to local hardware running, because you can, like Bowen mentioned, you are training the model sort of kind of through inference, because you have to do all these things called rollouts. And that's one area where, that there'll be more meaningful ways for people to use their at-home compute to contribute. But the data set curation, in the future is going to be a very big piece. We've seen already empirically, basically, that you're more or less only as good as your data, and the architecture is kind of like the salt on top, but like it really doesn't make it, and the data is what's there. And as we get through that, that'll be a place that I think would be much more amenable to having other people invest, be involved. We had a compute pool that we opened up previously to raise some money to fund this first DevNet run. And as we continue scaling out the network capacity, which we're at now, we'll be looking also to open that up as well. So that's where basically we're going to be looking at it. And I'll add one more comment too about like the fact that right now, you need these data center computes, GPUs. This isn't necessarily like, this isn't like something that has to be the case. It's an artifact of the current models that we know how to work. But what we want to be able to foster by creating the world's best AI in the open are those novel research outcomes that actually slash those laws, right? Like there probably is something out there right now that if someone, a new architecture that someone could discover that would be highly amenable to completely distributed training, without like even maybe like long-term weight updates where you can go forever, or merging the model like at where you can train a local piece by yourself and then it'll just sort of inference as the global sum of all of them. Like there's no reason these things can't go happen. But centralized companies aren't really going to be looking to solve those classes of problems because they want the IP that they create to be controlled by themselves, and a decentralizing force is a competitive force to them in that case. But what we want to do at Nous is to create the environment both from the availability of the compute and also from funding the researchers to take these sorts of foundational breakthroughs, like what we did earlier with Yarn, with Distro, some of our other methods, and foster that out into the public and make it actually also, financially viable for researchers to actually publish these sorts of results, work on distributed training systems, distributed inference systems, new model architectures that are amenable to distributed systems. That's part of what comes into that mission of creating the world's best AI in the open.
Jeff, there's a really interesting question here I'd actually love to get your take on. Evie asked, in 6 months to 12 months' time, what do you expect will be the biggest need for community contributions on the ecosystem and application side, and where can developers contribute in those areas without duplicating work planned by core team? Because I know
Yes.
we'd love more source code
Yeah,
contributions.
well, I could tell you one area. So we really recently, about 2 months ago, we did a hackathon in San Francisco on Atropos, which is our reinforcement learning code base. And that's like 100% our from scratch reinforcement learning code base. And in my opinion, like not to our own horn, but like if you stack up the features, I think it is by far like it is the premier RL package that you can do out there, at least that's at least open source. Inside of there are these things called environments. And the environments are kind of like, you can think of them like mini games, right? Like every environment is basically someone who coded up. Here's the rules of some situation, and LLM figure out how you can solve it. And I'm going to tell you whether you're winning or losing at this concept, right? So you can have an environment for Minecraft. You can have an environment for Hangman. You can have an environment for solving math problems using lean. You can have an environment, and so on and so on and so forth, right? The more of those that we have is only going to contribute to when we take Atropos, we bring it onto Psyche, and we do the reinforcement learning, at scale on Atropos as well. And that will port right over. So one area that's sort of like helpful but non-blocking, or is like not in the core path, is not in like the direct deployment path, I would say, would be doing things like increasing the Atropos environments, because those are going to then power the RL phase of this model. If you remember earlier when I showed you sort of those like 3 phases, you got your foundation model, maybe your fine tuning, and then your reinforcement learning. We know from DeepSeek and from other people that like the reinforcement learning scaling, we're only at the beginning of it in a lot of ways. And so there's a ton of green grass. And previously, people would talk about would open up their methods, but there's a highly competitive world out there right now, and people are very no one's open sourcing all their novel RL environments, and we want Atropos to kind of be like the centralized place where all the world's best RL environments can live there, and that will directly translate to Psyche.
And something that's really cool about Atropos is that, when you think about machine learning programming, I like to think of terrifying math and lots of PyTorch and CUDA kernels and stuff that I don't really understand. What's sick about Atropos is if you can write like a little game with some rules, right? You can contribute to Atropos. You can add a new task for the model to learn, and you don't have to know very much about how machine learning works under the hood at all, as long as you can give like build an environment for this model to play in, to learn, to try, and a way to tell the model if it succeeds. If you can build a game for a human to play through a computer, you can build a game for a model to play and learn from as well. So Atropos, I'd say the bar to contributing as a software engineer who doesn't know a lot about ML, that's easily the best way to get in and be able to contribute to the future of these open models that we're all building together.
Another place that people can use if they're interested right now is our API, which serves all of our models. So we have an inference API. If you go to the website, you can click on the API portal. This inference API is currently like we run it ourselves. It's centralized, like we run the inference ourselves. But it is designed right now. It is designed so that we'll be able to seamlessly roll that backend that's currently like running on centralized compute onto a decentralized inference substrate. So as Psyche evolves, we'll be routing some of those inference requests to the decentralized network, right? And then, that is one way by using the model, but it is going to our API and using the models that we have, that will increase the demand for the inference on the network. And then that's one more way that if you're interested in like helping out or like, using and contributing to Psyche, using the models through the Nous API will eventually get routed on to Psyche and then help support that as well. So that's one more way we can also do it.
I've also seen a lot of people ask questions about how, say they're working on a master's, say they're in grad school, how they can contribute some of their knowledge in the ML fields to some of the problems we're working on more on the research side. Bowen, I know we are running a researchers in residence program. How can people get their foot in the door if they have some super cool ideas, things they want to test out? How can they collaborate with us and build out, some of this fundamental research?
I mean, they could send an email to the what was the email? I'm not like totally
I don't know
I
either.
don't remember totally, but yeah, like you could send us an email and we'll look at the project.
Yeah, and we would love to, if you're interested in contributing some of your time and do some research alongside us, we are absolutely interested in working with people to further some of the stuff we're doing, or maybe if you have a really interesting project, shoot us an email. Yeah, there we go. careers@newsresearch.com.
Yeah, this one.
And while, as far as I know, our papers haven't gotten published in any journals, we do get cited quite a lot. If you look up Technium and Bowen and Jeff's names all over, we're all over archive.
All right. Well, I think we've had an hour here, so I think we could probably maybe are there any other questions that we see that we want to take? Other than that, let me see. I'm just going to scroll through. Anyone have any more? What are your hardest problems right now? I'll say our core blockers is really just the stability of the decentralized communication at scale. The internet is a fickle beast, and we have to optimize our distributed the networking stack to deal with this, highly heterogeneous networking situation. And we also offer optionality. Nodes can come in, they can leave. Each node has different, upload speed versus download speed, figuring out who should be connected to who to optimize that networking mesh. That's probably like the most difficult problem that we have. As for what we're working on, a lot of it is, I went over the PRs before, they're just more, engineering stuff, people who know Rust really well, who know Torch really well, who know Python. Knowing all of them together is kind of like, special. So people who have that code base, that experience are really helpful. But our core blockers right now is just doing whatever it takes to make the scale get bigger and bigger and bigger. Attention may be all you need, but scale certainly helps as well. All right. Well, I want to thank everyone for coming. It was great to do this. We're going to try to keep doing this every now and then, and especially as we gear up towards the mainnet launch. We want to keep everyone up to date. Be sure to star like the repo, check out the PRs, check out the issues there. That's where literally everything we do is there. There's no like secret repo or anything like that. Like all of everything we do is all right there, including our Atropos repo, our Torch Titan fork, all of that. It's open source, and let's build the world's best AI in the open together. So thanks everyone. We appreciate it, and let's do it again.
Thanks, folks.
Thanks.